Hello, I'm Ethan Frey. I'm the creator of CosmWasm, and I was also writing the IBC white paper in 2017. And these are two things I'm really, really excited about. So yeah, I've been hot on IBC since 2016, and I've been hot about CosmWasm since I wrote it 3 years ago. And these are amazing. Today, I'm showing you how to bring them together. We have multiple mainnets. There's almost 20 mainnets, I think 20 mainnets now running CosmWasm and IBC together. And we can start really connecting contract calls between multiple blockchains. This is an alternate way of writing Go modules. You can argue which is better, but CosmWasm contracts are by far faster to deploy them. You can write and deploy both sides of a contract, deploy it to one chain, the other chain, and immediately have a new protocol running cross-chain in a matter of minutes. The deployment speed is incredibly fast, and you do not have to wait for another blockchain, two blockchains, to do hard forks. So I'm going to show you how you can do that today in this hackathon, but also those techniques can be used to add things, making Juno osmosis connections in a matter of, write it and deploy it within a week or two. So I think this will allow a whole new era of IBC experimentation. And those experiments that become very successful may eventually port it into Go modules and reach all those non-CosmWasm chains. But I want to show you how to make this. To start, I recommend this GitHub, check CosmWasm resources on GitHub. You can follow along. All the links I'll be showing at this talk, almost all of them are on that page. So you can follow along locally. You can check the code out. I'm cool if you're looking at your machine, not me. So yeah, please check this out. The main point here is we talk about the beginning is how to use the CosmWasm Academy, the docs for it, the book for CosmWasm. These are great resources to learn in general for CosmWasm. And yeah, if you're interested in the CosmWasm Academy, please come by our booth over there and learn out more. We have a large series of videos there. You should be able to access them. 6 videos to learn Rust, learn CosmWasm in Rust, and get going. So they're available for everyone starting today or yesterday. We opened them up. So really for this hackathon to help you all learn CosmWasm as fast as possible. Now jumping to IBC. I want to explain a little IBC. So thank you very much for that last talk. It was amazing. I was wondering how I could explain IBC in the beginning intro, and you did an amazing job. So thank you very much. Thank you for that talk. I'm just going to do a brief recap of some key points in that talk, and then show how you can deploy them into making an IBC contract. How the interfaces are for writing an IBC contract in Rust and how that works, design-wise. Then we're going to look at simple code to see the interfaces. That should be the first hour of this talk. The second hour, I go into a real use case. The real use case, I wrote basically interchain accounts as 2 contracts. You can deploy a host and controller on 2 CosmWasm-enabled chains. It's basically the same design as I have there, a slightly older version of interchain accounts. I wrote this thing in January 2021. So I just refreshed it the last 2 weeks and updated it. But it's not just the 2 contracts you have. It's showing you how to do full stack integration tests. So it's going to launch multiple blockchains locally in the CI environment, and it will run node tests to quickly create channels, create connections, move packets, verify packets, and execute CosmWasm contracts in CosmJS and TS Relayer. So this is really, really powerful, so you don't have to test those command line tools. I've written bash scripts for testing. It's painful, and parsing JSON in bash and forming JSON in bash is not fun. So we can use Node.js and TypeScript to create really powerful testing environments and use all that tooling to really leverage that to do cross-chain tests of your contract, to quickly deploy contract to 2 local chains, connect them, run packets back and forth, and verify that it did the proper state changes. So I think this is really going to revolutionize the act of writing and testing, especially IBC contracts, and give you a factor of 10 speed up possibly from the current way of doing it. So I want to introduce that today, share it with you, and hope someone can build something in this hackathon and beyond. So if you look at this, this is from the IBC spec. Basically, this is a recap of what I was talking about earlier. You have a client and a connection between 2 blockchains. Let's just use Juno Osmosis. I use them because they're 2 major chains in the Cosmos ecosystem running CosmWasm. So you can deploy to those 2. The hub is the largest one, but it's not using CosmWasm. So I'll just look at the other 2, number 2 and number 3 in the ecosystem. So yeah, imagine you have Juno on the left and Osmosis on the right. You make one connection between them, And on top of that, you can connect many other things. There's already a connection there. And you will then make like a port here. To connect this one is transfer to transfer. So you have the transfer port. You connect it with ICS-20 to make a protocol moving money back and forth. In the meantime, different contracts can have different ports as well. And other contracts here have ports, and you can connect those. So you connect those things between these different contracts, the different ones, and you have multiple channels running one connection. Once you establish a connection, which is a light header proof, you just have quick channels. So look at the life cycle here. A channel basically, and this is where the contracts come in. If you upload an IBC-enabled contract, when you create your contract, it will automatically reserve a special port for you. The port name is wasm.your address of the contract, so it has its own unique port name. And once you have that port name, you get in the beginning. Then you make new channels, so people connect you. You connect a contract to another contract. And this is the state. Basically, there's channel initialized and channel open try, which are the first call on A, the first call on B. Then there's open ACK and open confirm, which is the second call on A and B when they agree. So the first two are really to verify they're the same version, they actually know what they're talking about. I'm not trying to connect ICS-20 to Interchain accounts and they go, who are you? So the first two, this first step and the second step here, are really to verify the other one is talking the same language as you, the same protocol, and you're compatible. You do that version negotiation. And once you've both said, yeah, you're good, we like it, then with the second stage here, to confirm it and store any state changes, oh, it's really a connection established, I'm going to store the state change here locally and do any initialization I want for that connect channel. So we expose this to the contracts as two different calls. They have one call which combines these two, the first attempt, and one call combining these two. These are basically the same, just the A and B versions of those. So we expose those as different calls to the contract, and we also expose the close. When you close at the end, there's another call. So there's three calls to the contract, which is start open, confirm open, and eventually, possibly or never, close, which are channel life cycles. We expose those to the contracts. If you have an IBC-enabled contract, you must expose 3 handlers for these things. They can be do-nothing handlers, but they must exist. The other part that happens is the packet lifecycle. Once you've established a channel, you move packets back and forth, as you saw in the relayer demo of moving data back and forth over the channel. This whole app here is send packet, query packet, receive packet. You see this whole process here. You also have a few callbacks to contract in this lifecycle. We use all of the standard IBC Go libraries, the client library, connection, channel, port, all the infrastructure has been heavily tested, built. It's amazing infrastructure, and we build on top of that. We don't replace it, we build on top of that. So we just give a few hooks it gives us for calling on the channel lifecycle, starting, confirm, end. And once a channel exists, we have a few more hooks. Once a packet is received, we have a separate message here. So if you have an IBC-enabled contract, you can do send packet, which allows you to send a packet, a new packet of any format you want. It's a new message format, Cosmos Message IBC send packet, which will send a packet on a channel that belongs to your contract, right? Only your own channels. You have one port, so any of those channels that belong to your port, you can send a packet on it. The other side will receive a on-receive packet callback. That callback gets the packet on the other side and returns acknowledgement or an error. Success or error as you want. So that's side B will get that. So side A will call send packet. Side B will eventually get this callback, the receive packet callback. And then call app A will get this on acknowledge. So it will get an ACK containing the original packet it sent along with the data that came back from side B. Usually if you send packet, you should expect acknowledge packet. However, sometimes it does not get relayed. Maybe the chain goes down. Maybe the relayers go down. Maybe gas fees are too high. The packet never gets there. So there's a timeout, you mentioned, and the timeout packet will get called. So you're guaranteed to eventually get something back. Either you get an acknowledge packet containing a success or error message in whatever local format you design, or it never happens, it never gets over there, so you get a timeout message. So there's 3 more hooks we expose to the contracts, which are on receive packet, on acknowledge packet, and on timeout packet, which we'll send to the contract. So when a contract makes a new channel on its port, all those packets on that channel will trigger callbacks on that contract. Do you understand this? Am I speaking too fast? Please speak slower. So those are those callbacks. You can look here. Another thing, this is in the resources directory. This is linked there also. You can type it in now. And CosmWasm Resources has a link. This is a spec in CosmWasm of how to build IBC contracts. It's maybe not a good introduction, but it's a very good reference. It explains all these pieces. So I explain how you can send a transfer message using ICS-20. We built in as a native call. And we explain how to write new protocols. This explains the channel lifecycle of open and the interfaces for it, the channel connect interfaces, and the packet lifecycle with these callbacks I mentioned. So this is a reference here explaining what I just talked about in a little more depth. So I highly recommend this repo. This thing is linked also in resources. You can refer to this if you don't remember what I said, if you want to read a bit more and see those code of what interfaces are needed for a new contract. So that's basically what you need to know as theory. I'm now going to start looking at a contract. This contract is a nice one, not mine. It's a nice guy from Juno wrote this, Zeke. And I was writing one, he shared this thing, and that's awesome. It's a really, really simple contract, which is why I like it. It's Mint, so you just, it's not a multi-repo, nothing complex. It's the simplest CosmWasm contract that is IBC to learn from. So this is a great starting point. If you've ever used CosmWasm, there's a CW template we have, which generates a simple app, which basically is a counter. That you have messages to like update a number, what the number is, update it, what number is. I mean, it's a pretty simple app, but it gives you a framework of building more complex apps. This is the same thing in the IBC world. So you can look up this repo here. It's Ezekiel CW IBC example. I believe I've linked that also on the resources page. So you can see it here. This one here, simple example contract. That's where we're at right now. If you're following along, I just did a quick run through the theory because it was covered in the last show. If you're watching at home and missed this first part, look back an hour and a half. It was an amazing talk. Beyond the IBC contracts, we're right here now, if you're following along. So this is a simple example contract I want to show you. This one basically, you create the same contract in two sides, and then you call increment on one side, and it will create a packet. And that packet will go to the other side. And then you can query them. So you have two direct contract calls. One calls increment, and the other is get count. But increment does not increment that contract, it increments its partner contract. Yes? So when you call increment, it will send a message to the other side, and the other side will go up. So I can create two contracts. I tell A, increment. It sends a message to B, increment. It gets a message. It says, OK, I'll raise my number by 1, and say, OK, I'm done. And then over here, the number should go up. So it's a very simple example. It's not very useful in the real world, but it helps you understand the basics. So it explains a bit here about introduction here, the init, and the handling messages. So again, this is a nice repo. If you want a simple example, I'll cover it. You can refer to this as a very simple example of an IBC contract. It's the smallest possible one I've seen. And inside of it, you can look at the entry points. So I'm going to start here to kind of make a not very scary version of using IBC contract, right? So it's just a few things. You have this funny line here. Just copy it everywhere. Entry point means we expose it in the WASM blob. And this CFG after not feature library means if I import that contract from another contract, I don't make an entry point. Entry points means actually the WASM that's compiled with it will expose this as a command that the VM can call. But you can't do it twice. So if I have an IBC contract import another IBC contract, and they both try to make entry points, they'll make two entry points with the same name. It conflicts, doesn't compile. So we have this library feature thing that turns it off, basically. So you don't really know this. Just remember, put this line above all those calls. Just copy that line. We use it everywhere in libraries. Just copy that line. It means make it an entry point. Expose this one, please. You must use the exact same function signatures here. And if it doesn't, again, the compiler will give you some error. It might be a little opaque error saying does not match, something does not match something. But basically, you have to use the exact same definitions for it to work. Yeah, so here's the deal. IBC channel open. What it does is we say opening it. And the relayer first is we're going to open it. It calls side A. Open with this version. And it verifies the version is proper. Right? Let's see if the version is okay. And the ordering is okay. Are you ordered or unordered? What the version of this protocol we're using? That's the first step. And then after you do that A, then we call this on B. Okay, is the version right? Very good. After that is done, then A it calls IBC channel connect. That can again validate the order and versioning. Because if A starts a version, B gets another one, it returns a different version, it can negotiate versioning, and it comes back with a different version back to A. So you want to double check again here to make sure that B is not changing the version, right? I say I want ICS 20-1. This one says, no, I want ICS 20-2. That's newer. And it comes back here and you say, oh yeah, okay, that's cool. I can use ICS 22, or no, I can't. So you want to double check that also in the, on the third step. So these validate order and versioning is a very nice thing to check. We do a lot. And then after that, you can save the state, because now you're basically guaranteed both sides agree the channel is valid. We can use this channel. It makes sense to you. We know what we're talking about. We're using the same IBC functionality with counter 1. We're talking something we know. So we have the same protocol. This is a handshake for the protocol, which API we're using. And then you basically here it saves some information of the connection, the channel and the number of connections. So then on close, whatever happens, what it does here just deletes the channel from store, which is simple cleanup. But every application needs to do when you destroy that thing, you can do some tear down logic at that point. So these are just hooks you can use. They're usually pretty simple stuff. They're just basically, check the order versioning and set a little initial state for this channel. It's simple stuff. These are your hooks. The more complex stuff happens in the packet lifecycle. This is really where you combine execute and query locally as remote functions. So you can see the IBC packet receive is what happens. We sent a packet and it gets a packet. So you parse it. And actually this code is based a bit older of my stuff. So you don't need these two functions to do it. Anyway, I'll explain later. The newer version, but basically you have this, you get the message back here, you parse the data, and then you can match on it. If you just CosmWasm, this is just like how you do for execute messages, right? So I received a message on my channel, some message on this channel. I know what channel it comes from. And then I can parse this message into an IBC execute message and then see, okay, what is it? Oh, it's execute, great. If it's something else I don't know, then I return an error. But that shouldn't happen because we agreed on the protocol already. So they should have the same protocol. So we have this, and you're talking to a known party on the other side. Anyway, you have this. This is where you parse the data and dispatch them on IBC receive. And you see here, basically it just does this same thing. It says, okay, increase the number by 1. This is update number and make it 1 bigger. Unwrap or default by 1. So that's pretty simple, right? If I receive a packet, it says, parse it, and it says, okay, increase number by 1. That's very simple. And it can return some data. So what it does, it returns, when you create the response there, you need to return an acknowledgement packet. And this one has basically make act success. It's an empty packet saying everything is good. And if it fails, is a packet here saying everything is bad. So you define the shape of acknowledgement packet on your code. The same way that you define in CosmWasm like a query message and a query response, you can define an execute message, a packet type, and a acknowledgement or response type. It's an enum in this case, if you need it. So here we have, so this is called here on receiving a message. This is when it happens. When it's finished, it gives an acknowledgement that comes back, and it calls on IBC packet ACK, which does nothing with it right now. This knows it could parse this if it wanted to, and determine whether it failed to succeed the other side, right? It could actually, it knows the original packet it sent here in this message, and it also knows if it failed or succeeded. So you have this information available to you, and you could do something, in this simple example does nothing, but it's a placeholder for you to add. And on timeout, you also know that the package never got anywhere, and usually you want to handle timeout and fail the same. So if I get an acknowledgement of a fail and a timeout, I usually treat them the same way. It's garbage, nothing happened. And success is a different way. But some protocols want to care about all three different cases, so you have all three exposed to you. You can decide what to do with it. These are all the entry points you need to write an IBC contract. It's not scary, is it? It's just, we've looked at like 100 lines of Rust code. Most of it comments and function definitions. But yeah, this, that's all it is. This contract, when compiled and uploaded to Juno, will immediately make a port. It'll bind a port. It'll make a new address and bind a port. And if you deploy another version of Osmosis, it'll bind another port. If you create a channel with the right version, if you make a channel with there, counter1 as a version, and what valid, it needs unordered. So it needs unordered channel, and it needs a version of counter1. If you try to connect to the wrong version, it says, can't make a channel. If you try to connect to the right version, it'll say, great, make a channel. And then you can call increment here, the number goes up on the other side. Any questions on that one so far? There's one more piece here to this repo. So the IBC directory here, there's the contract. So how do you actually create that first packet? We talked about how to receive the packet, but how do you create the packet? So execute, if you call increment, this is a really small function. So when I call increment on the first, not the message, but like the normal execute. So when you call a contract, you just call it directly as a transaction. Say call this contract and give an increment thing. It will make this message call. If you know CosmWasm, it makes sense. If not, maybe not so much. But basically it says, do an IBC message send packet, given a channel I own. It sends this message here, right? Which is the increment message you saw parsed on the other side. So we can use any message you want there. And this is basically what we're executing on the remote side, the packet we send to the remote side, the data value. And this is a timeout. This one says timeout in 5 minutes. So if the relayer is not running, you forgot to run a relayer on the channel, and no relayer moves it, 5 minutes later you can time it out, and you can say, hey, it's dead. You start your relayer, oh, I forgot, I'm late. 20 minutes later you start your relayer, it'll time out this packet, and it never happens. So you know it timed out. So you can set the timeout you want here, you set the message you send to the other side, and the channel you send on. So you have to send a channel you've already created yourself. You can check that if you want here. You could actually assert that channel is a connection I know, not some arbitrary channel. It doesn't really matter, because if you try to send a channel that you do not own or does not exist, you'll get error anyway. So you can check it locally or just send the message and see if you can error on it. The whole IBC runtime will check all this stuff for you. And query, the rest of the thing is, so once I've called increment on side A, it creates that send packet. That send packet is relayed over to chain B. Chain B then processes that number and increments the number 1, right? And so returns an acknowledgement. How do I know it happened? Then I go into chain B and I query count. I do the get count call and I get a response with the number that happened. So I can see it. So I can call a message here. When the relay finishes, I check on chain B, the number did go up. I know it worked. So right here is the entire life cycle. In a little bit of code, check that repo out, read it. It's a very simple CosmWasm contract. A lot of the stuff that looks like scary stuff is really just boilerplate. I mean, you have these function arguments, they're all the same arguments. It's just a set of arguments here, right? Like all those lines are the same thing. And it says, okay, this is the whole logic in the function, which is just put some log messages on it, emit some events in Ethereum terms of emit these events, and send a packet. I mean, that there is 8 lines to send a packet. It's not hard at all. So once you learn the CosmWasm framework, this is not a very complex contract, but suddenly it's a cross-chain contract. The hard part really is designing the protocols. So I'm trying to show you that the interfaces are pretty simple. There's references, you can look at examples to learn them. It takes time to learn them. You don't know them. But once you see them and play with them a little bit, they're not that complex. The hard part is designing them properly. The protocol design. So before you write this one, you can draw a piece of paper. I have 2 sides. I send a message here, here. What messages can I send over here? What happens, right? This one is a very simple message. All it does is change a number. But if you're changing state, if you're locking up ICS20, you lock up tokens here, then you send them over here. This will release the token over here, right? If it sends it back the same token in the same channel, then it can release this original token. If it's a different channel with the same token, then it reject it, right? That logic here. If the transfer gets a failure message back or times out, then it release those tokens because it never went to the other channel, the other chain. So that's the logic of ICS20. You can probably write it down on draw a picture of paper, one sheet of paper, and try to draw that down. It's very simple. They have one type of message, back and forth, and you can probably draw that one piece of paper. If you have a more complex one of locking tokens and doing complex stuff, it's a little more complex. But I think the protocol design really is what you think through, all the use cases, flow diagrams or protocol diagrams. And that's really the hard part in this IBC for me, is designing it, thinking what it should be. And once you have an image of how it works and know how it should work, writing that code should be as easy as possible. I want to make nothing as little as possible stand between your ideas and the code, and then the code and production in mainnet. We try to make that whole process as fast as possible, and the hard part becomes thinking of and designing the image in your head of what you want to create. That is hard. That is very hard. But the rest of it, we're trying to make it as easy as possible, and I cannot help you with designing the protocol so much. I can review your protocol if you want. If you have an idea, I can review your protocol idea. But really, once you have an idea, you can write down your idea and show me your idea. I can sit here, I'll be here today and tomorrow. I can help you write it into code and help show you how to tips into writing the code and actually making it live. So yeah, that was nice. I thought I'd have much less time because I expected this to take an hour of a lot more explanation of IBC. So thank you again. And I have a little more time to actually dig into a deeper contract. Yes? You're right. So packets here are not like a TCP packet or something. They're broken chunks. This packet is basically like a JSON RPC call or REST call. You can imagine it like that. One packet represents basically, if you're used to JSON RPC or REST, anything, it basically includes first all the metadata, the header metadata that proves authorization, all that stuff, along with the payload, which is actually the message being called. And that whole authorization mechanism, so we call that a packet in this term. I didn't invent that word, but it's a packet. This pent along a channel is basically one call. And all the metadata of channel, light client proof, all that stuff is handled for you behind the scenes. That's the header kind of stuff, the authorization. And the data of the packet, the data part of the packet is this message, this execute message increment. Is it just, we put the data, we set the data value of that, and the rest of it's handled by the framework. We don't touch it. So once you've established it, this is the metadata, and that data packet you pass there, and the response value also is header metadata, which is validated on this side, and the JSON data inside the response, of the HTTP response, is basically what we get as acknowledgement. So I think that's a better term, and hopefully that makes more sense, because yeah, packets are very low level. Does that make sense? So yeah, I really think it's basically JSON RCPC or REST, something like that, with HTTP headers as authorization. Cool. I have one more thing. So just before I go into coding and open up my editors, I'm going to show you this one, CosmWasm testnets. So you can check this repo out. We have 2 testnets live, Ibiza 808 and Malaga 420. We did a team retreat in Malaga, so we decided to make some testnets here. And we said, hey, 1 testnet is fun, but 2 is better because we can do IBC. These are not tied to any mainnet. They're not Juno or Osmosis or Cosmos, nothing. There's no mainnet. They're just 2 testnets run by us at Confio for all CosmWasm developers. They have nice faucets because no one really cares about these test tokens. They're worth nothing. So we have faucets. You can hit them with curl. We have nice definitions here. You can look inside. And basically, we define where it is, the RPC endpoints, the PDP endpoints if you want to run one, and some defaults that let you configure this up. So you can see where all the things come from, and you even see where the faucet is. And this is a faucet we have, which you can load from a curl command. You can get tokens in a curl command, and there's actually a CosmJS faucet client library that just give this URL and it'll get you money. Just give you money. Yeah. So our testnets are meant for CI basically, and for scripts, so you can just automatically do it. TS relayer, if you can figure out the faucet URL, it will just, when it starts up, if I have no tokens, I hit the faucet to get money. So it'll self-feed itself from those faucets, which is great for testing. So you can actually test these testnets. TS relayer will fund itself. Don't worry about funding itself. Makes it easy. So yeah, you're welcome to deploy, and maybe you actually need to deploy on Osmosis or on Juno testnets for the winner. I'm not sure, but at least you can use these for early on starting. I think they're nice, simple ones. Yeah?
So we have the same, in the counter, we have the same smart contract at 2 networks.
Yes.
So it's bidirectional, the agreement. And outside of the example, is it unusual to have the exact same smart contract on network 2 networks we want to do?
It's a possibility. So if you look at ICS 20, it's the same code on both sides. That's completely symmetric. The Go module, there's one Go module, which is IBC transfer. And that's the same on both sides. They both know I can take my local token and send it over a voucher. I both know a remote token comes back to me, I mint something, or my remote token that I sent earlier comes back to me, and I then release it. So that logic is the same on both sides. It's symmetric. So token transfer is fully symmetric. ICA accounts, interchain accounts, has a control on a host side because A is controlling B. It's a unidirectional protocol. It's an asymmetric protocol. So both of them exist. Interchain security example, there's a controlling chain and there's a baby chain. The parent chain, the baby chain. I don't know what they're using these days as names, but they use it for a while. So one of them controls the other chain. It's very clearly asymmetric. And so other than a transfer in this example here are bidirectional. You can choose that. I'm going to go into a code example, which is asymmetric as well. It's based on interchain accounts. It was back in early, so when I wrote CosmWasm in a hackathon, that was in Berlin, 2019. And Tony from Chainapsis, Kepler, Osmosis, doing amazing work there. He actually spec'd out interchain accounts as a super prototype in the demo. Then he got very busy writing Kepler full time and didn't really build it out. And, but I thought it was a really cool idea. So when they started building out IBC, I need a test contract to test it. I built something called IBC Reflect, which is basically loosely based on his prototype definition. And I wrote this thing and stuck it there as test contracts we stuck into a WASM VM to verify that our bindings worked and we could actually run this stuff. So we used it as a test contract just in our CI, never in production, never for anything. So I built this thing, and the last few weeks I basically pulled this out, brushed it off, updated it to IBC v3, cleaned up all kinds of stuff that was like these old ways of doing things and try to make it more modern. But now it's the same idea basically. It's a loose idea of ICA accounts. I call it simple ICA. It doesn't do everything ICA does, but whatever. It's the same idea, the same general theory that you learned an hour ago about interchain accounts. And it has a control on a host side. I renamed the two sides also based on the newest name. So I try to clean it up so you're more understandable to modern development. And so that's what I'm going to show now as an asymmetrical protocol that's actually live. Well, actually works. So not live anywhere. I've only deployed it on my local machine. So I haven't actually seen these contracts in any testnet even. Yes?
What is the easiest way to test our ABC contracts?
That's where I'm going to go. Thank you very much for that question. It's a great question. There's two ways of testing them. I'm going to show you can write some Rust tests. They test basically the unit tests. Yeah. So you can test one call. So you can test the send part. My method sends a packet. I can sort of see that if I have a packet over here in this format, it will parse it properly, right? I can then fake an acknowledgement and do it. But I cannot do the whole flow because I'm just unit testing it in isolation. We don't have any mocks to mock up two blockchains to connect them with real IBC and all the whole handshakes. So we're basically mocking little pieces, unit testing them in isolation. That's what we're going to do in Rust. I'll show you how we're doing that in Rust here. It's a very good question. I think it's a very important question. What I say is that's not enough. And so another thing I spent the last 2 weeks doing was brushing off the TS relayer, TypeScript relayer, which I also wrote back in early 2021. And that one's a TypeScript relayer. It's not just a relay like Hermes. It's really a library. wrapped as a node command. So that library now can be imported and very quickly write TypeScript tests. So first I'll show you the Rust code to use, and then I move over to TypeScript. So if you're front-end dev, you can ignore the next half hour, and then I show you the front-end stuff, which is really just TypeScript, very high-level tests saying I load up one doc image with Osmosis, one doc image with WasmD, Juno. I then have a CI test. It says install this contract here, this here, create a connection, create a channel, call a command, send packet, relay packet, get result, relay ACK, do that, and verify the state. So that whole process you can do very quickly in a nice, just whatever test run you want. Use Jest, Jasmine, whatever. So that's, for me, the best way of testing this stuff. This was not done or documented until recently, except buried somewhere in the ICS, in the TS Relayer repo, which I understood. I used it, but it was not accessible to anyone. So I spent, again, the last few weeks pulling this out of the repo, extracting it in the simplest way possible to use a template. So I'm showing you now that first contract I showed you is a template to learn IBC. And this is one repo, which I think is a template for building your own IBC contracts. You can copy this one as is and rip it apart. You might want to just copy this one and then fork it and modify it if you want to do it, or just copy it directly and then completely change the underlying thing. But that structure it gives you is a structure to create two contracts and then a CI that will run them. So this all in one repo. It's both Rust and TypeScript. I'm going to look at the Rust side first. If you look here, it's a standard multi-contract repo, standard, like CW Plus or many others. It has two contracts, simple ICA controller and simple ICA host. It has one package, simple ICA, which defines the protocol itself, the shared library that they both use. And it has a little function, a repo thing called tests here. Test is actually just a package JSON. It's a node app here. It's a little node package, NPM package here. And this package, JSON has a source file here. I'll open up later in something else. And a controller calls on the spec, and you see these tests here. Everything that shows basically a bunch of code here that just says upload contracts to WasmD, upload contracts, step channel with ICA 20 contract, whatever, ICA, connect account and send tokens over. So we have just simple tests here you can run, assuming you have local networks. So I'll go into this TypeScript stuff later, but this really is really interesting integration test for me. And once you can do this, you really have the same code here in these test cases as you'd use in client setup. So if you want to deploy contracts, you can use the exact same code. You pull into a script saying deploy. Deploy.ts can be a CosmJS thing, which will actually load contracts on multiple blockchains and instantiate them with the proper values and create the contracts. So the same code used in CI, you basically pull out into a script and use that same code in a script to deploy it and to execute it. So I think this is really nice for here because I find bash scripts really hard again for interacting with things. But I'll get into that later. So this is the structure I'm proposing. This is not like the Bible. This is not something I've worked on for 10 years and said this is perfect. This is my current iteration. I took up some old code I wrote. I cleaned it up as much as I could in a relatively short amount of time. I think it's relatively clean code, and it presents a way of doing this. If you think the abstractions here are bad, change it. These patterns I'm using are decent practices. They're not necessarily best practices. The patterns in CW Plus, I think, are pretty much best practices. We've tried them for a long time. They work out quite well. These are still newer, so I'm very happy to have them challenged. PRs can improve the structure. But at least you start with this, understand it, and if you find it limiting at some point, ask me. We can make them better. What you define here is basically the packets. So the packages, so not looking tests, I'm looking in packages. So I have a shared package called Simple ICA, which has basically a few things. It's a library that defines the constants, and we use unordered channel, and we use Simple ICA v1. It defines some constants to share them everywhere. It defines a few checks, some error messages we can use here, and check order and check version, right? We talked to the other function, assert order and version are correct, and this does the same thing, straight up, right? So we make some simple helper functions, so they both wanted the same thing when they check it. If you have two different contracts, they want to share the same logic for validating the version and order. And the main thing it has is actually defining the common message passing structures. So we pass packets. This is what's common between the two sides. This is not their personal interaction to execute messages, instantiate messages on the contract. This is the wire protocol. This is the inner blockchain communication protocol right here. Packet message is the message that is being sent from the sender to the receiver, right? So when you send packet, you're sending this one and receiving this packet. And it's just like this. We have 3 different versions here. Dispatch, which says run these messages. Who am I? Finds out, given a channel, what's my address. And balances gives me my address and how much tokens I have on the chain. It's a useful query. So we can make it a better one with more queries, more things, but seems decent stuff here. For that, so I think the main thing to think of here is if you look at it, these two would work as queries. If you look at a normal contract, these would be query message, and this is execute message. We don't have such a distinction in interchain communication because it's only a packet you send, right? Depends how we handle the other side. We don't have different entry points. We just have one way of calling it, which is send packet, and that's relayed. Over here, the other side determines what to do with it. And we define the acknowledgement format. This one's called std_ack. You can actually copy this code. There is an attempt to standardize acknowledgement format that was used in ICS 20, right? They have a kind of standard thing. It's also in some ICS 7 or 27, I don't know, some other one anyway. But this is basically defined as protobuf. But ICS 20, they use as JSON. So you get a result or you get error as a string. And this is a JSON format. I found that very handy for contracts, and we can use this one. There's one bonus of using this as a wrapper for acknowledgement. If you return an error on IBC packet receive, right? If your code returns an error there, you don't catch it, or a sub-message returns an error that you don't catch, and somehow that contract returns an error anywhere, we'll grab the error, we'll wrap it into this standard acknowledgement format as an error, and we'll roll back all state changes. So it will not fail the transaction will succeed, and it will write an acknowledgement error to the other side in this format. So as long as you use this format, if you do not want to use this format for errors, basically capture all errors, all sub-message errors, roll back and state internally, and you can define any acknowledgement you want. We did that before. It was a very hard user experience for me. I mean, I could do it, but I found it challenging, so I said, we're going to make it easier. And now we say, basically, just use this format if you're making new protocols and not trying compatibility. If you're doing compatibility with existing protocols, you have to do their format. But if you're designing your own format, it's your contract and your contract here, just use this one as acknowledgement, and you can return error anywhere and receive, and that'll automatically get wrapped into this acknowledgement packet on error and do the rollback state as you expect in a contract. So I made this one here as a few helper methods to create a success version. You'll serialize your data. And a fail, which will make the error message, and as an unwrap thing to verify it. So it's a really simple thing, but it's a nice little helper to use. I recommend using that in your own protocol. So even if you just want to use something else, you can rip out this piece of code here and use it. And the last thing it does is responses. So again, on one side, this is both message and execute and query. But like query, every one of them returns response data. Right? So when I get dispatch, I think of acknowledgement. So this acknowledgement contains, if it's successful, it's a result, which is binary data. It's a message. What is that? Well, it should be one of these things. It can either be like query, a dispatch response, if it's a dispatch packet, a who am I response, or a balances response. And that's what's passed inside the acknowledgement packet on the way back. One of these 3 things, depending on the type of packet. So this is the shared wired protocol they both use, and they just have this common data structures here. I found it a useful thing to have separated, and then you can just work on the logic separately. If I look at, should I start with the controller, where it starts? So the controller here, again, I'll go a little fast here. On open, just basically checks versions, it inserts versions are correct. On connect, which is the confirm, once it's established, the connection is established, it will do this, and it will, the controller will create an account data, basically an empty data saying, hey, we created a channel here. We don't know who it is, we create a channel. And interestingly, what it does is it makes a who am I packet. So when the channel is established, when we make a new channel here, they do this much fancier now. They refactored all IBC Go in a very, very complex way to do this in the version negotiation, do this inside of that one, which is actually nicer in a way, but super complex. And the simple way it had, again, worked a while, was just when you create a new channel, a controller starts, it tells host, I'll make a channel. Host says, okay, I speak your version. And then the controller says, who am I? Right? Who am I? And so then the controller, the host, when it establishes the contract, says, okay, when it establishes it, it will make a new account for you. It makes a new account for you. And then you say, hey, what's my address on the other chain? Because I need to know my address on the other chain so I can send money over there. We'll see how this works. So it does this automatically. It does a send packet here. You see this lines here to send a packet. Pretty straightforward, to lifetime. And then you just do add message to send the packet. And this is how it says, okay, send a who am I message on the connection. Close just does some cleanup. Then receive doesn't do anything because the receive part is not in the host, right? So let's look at the execute part here. So this is just the controller. So one thing happens when you create a new channel, it says, who am I? And there's a few more messages. It has update admin. It has send messages, which actually dispatches or wrote messages. It tells other side, do this on the other channel on my account name. Check remote balance. It's a query. It sends a packet to the other channel, the balances query, to find out how many tokens I have in the chain. It's a pretty useful query to have. And send funds is an interesting one, which basically says use ICS20, like a parallel connection, to send money to my account on the other side. Which is useful. So I can say, hey, I can make a connection. Then there's this packet, say, what's my account address? Great. So they do ICS20 to send funds over there. Then I can query balance. I have money. Then I can say, go swap that money, go invest it in staking, do what you want with it. So this is kind of the protocol. And query message, you can find information about your account on channel ID. An account will tell you the channel on it, the update time, it was updated, how recently we got the message back on the other side, the remote side, the address on the other side. So if I'm running on Juno, I have my Osmosis account here, what's my Osmo address, and the balance on the remote side. So that's how we execute it. In the contract, basically, you see those things handled. That execute message, send messages here. We'll basically verify that I'm the admin. My contract only called it one address owns it. And it just does the same thing. You see this thing, it just basically says dispatch. Take this message and dispatch them. And then add message of this send packet. So to send a packet is pretty easy, right? Just do send packet and you run it just like a WASM execute contract call. Same thing, check remote balances. We'll make a new packet called balances and send to the chain to wait for the ACK. Now jump to the host side. So we see how this works, the controller, how it sends packets in the beginning. Does this kind of make sense, how I've structured it? So it does first, it checks its own life cycle when it starts up, just initialization. But basically, anytime you want to, you can ask for check balances, and it'll query again, and when that's finished, you'll have a new updated data from the remote side. It's out of date. The number of days is all out of date. But you can ask again, and it will then later get packet back and give you new data of the new balance on the side. So you can see who you are on the other side, you see your address, and you can ask it to send packets over there, do messages. So if you look at the host side here, this is more interesting, I think. So we have the way we create new accounts is this. Every time you create a contract, it gets its own account. There's a very simple contract in CW Plus called CW1 whitelist, which says, let any of these addresses do anything you want as me, right? Basically it says, just you send a message to it and it repeats your message again with that new address. Reflect, basically. So what that does in this case, you could use it for like access control lists, allow 3 people to share access of something. But what we do in this case is basically say, our simple ICA host controls another contract here. It makes a contract, and that has its own address. And every time you make a new channel connection, it will make a new contract, a new baby contract. Oh, this channel called me, I'll send the message. I take it, I go to this contract, it sends it in that name, just one address. Another connects, I make a new address for them. So it basically manages to have multiple addresses controlled by one contract. So obviously, if me and Jake both connect to something, and he sends all his Juno over there on his Osmo address, I shouldn't be able to access that same thing and somehow steal his money. So clearly we have to be separated. We have different addresses on the Osmo side. We have different addresses on Juno side. So that's the reflect code ID. And we see here basically the host doesn't really have many entry points except for the open. Open here is checking, right? The connect here, what it does, you see this is, so when it connects and the connection is succeeded, it will make the instantiate message call. And that says make a new contract. We have the code ID to use a contract, it's already uploaded. And it says, okay, now this is even more hard. This is even harder, look at this. This is harder than sending a packet even. This is make a new contract. It's not that hard, but the sending packet's so easy, this looks a little bit hard. It says create a new contract with this configuration, which is listing I am the admin. Me, ICS host, is the admin of this other contract. I create this new contract, and they get a callback to find the new address. So we use the ACTO model. If you don't know CosmWasm, you don't call directly. To avoid reentrancy, you return messages. Those are passed. If you return messages, you can just fire and forget. If they error, the transaction is rolled back. You can also get a reply, so when it succeeds, you get a callback so you can handle it later on. So I finish my job, I say, do this. It runs that. It might run subcommands, anything it wants to. And eventually, when it finishes, I get a note, hey, it finished, and here's the data. So this is a good pattern if you instantiate. We do this thing called reply block. It's a bit complex, CosmWasm. And if you see this one, the reply init callback here, basically just says we parse the reply instantiate data and find the contract address that was stored there, find the contract address from the reply, and then we can store it here and make sure we have not stored it once. So it's a little checks here. But basically it says, okay, find the address of the new contract we just created. This is a pattern. It's medium, moderate, advanced CosmWasm, I guess. But so we use it here. So create a subcontract I control, I have the address of it. There are a number of people here in CosmWasm. They should be able to teach you this if you don't know. But what it does is, when the channel is created, I create a subcontract, there's a new address. I store that address, I say this channel ID 17 is connected to this new address of a new contract of mine. Right? Let's do this mapping. And that's what we do here, is account save the contract address. So I know the channel ID is mapped to the contract address. So I've stored that when I create a new channel. And now when I receive a message here, I'm going to stop going into the details here. But basically, when I receive a message here, it gets a packet, it parses into a message thing, and it dispatches based on the type of message, right? Just like execute does. We don't catch errors here because we just say they're handled by the environment now. This is new in IBC v3 that we can handle with the runtime. We just do the rollbacks. So basically, this is receive dispatch, receive who am I, receive balances, just like execute. Who am I? We just load the account, right? Find the account ID, the contract address for the channel, and return that number. Return it, and then we say basically make the response here, and then make a success acknowledgement for it. And then set ACK. And this is how we define basically, this is what he has data, we turn it to an acknowledgement wrapper, we wrap it up and then set the acknowledgement. And that will be returned back to the caller. If it is balances, we find the address first of all, like before, then we query the data of coin balances to find all the coins that the contract has, and then return it like here with a success and acknowledgement. You don't have to get all of this now, but I'm just going through it a bit. You can look at the code later at your own leisure. And finally, dispatch, which is more complex, which says basically load the account that belongs to it. We start with this empty result. We start basically with something saying we did nothing. You'll see why. And we have to give acknowledgement of something. And basically say, okay, now we find a message saying, CW1 whitelist, run this command, execute these messages on my behalf. So the host contract says, hey, baby contract I created, whitelist contract, run these messages on my behalf, and then runs them with a new address, with a unique address for that channel. So it looks it up basically on this account. So given this, this caller, this channel ID, what address do I have? And it says, hey, tell that contract, WASM execute, tell that contract to run my messages with no money. So that's basically a way it can dispatch with multiple addresses from one contract, which is a pretty cool trick, I think. And then when it succeeds, you get a response of what happened then. Receive this. So yeah, anyway, I get the response on all of that. Then, yeah, then ACK, we never get ACK or timeouts because we don't do it. And when we receive this stuff, so there's a reply dispatch one, which basically says find the result awaiting data. We get the data we got just from this callback. We get the data from that call, and we store it in a dispatch response. So we first set a placeholder saying we did nothing, and then once we get the result, we use set data to override the acknowledgement. So in the reply block, you can update the acknowledgement later on. So we start with an empty acknowledgement saying we did something, nothing happened. And then when something did happen, we say, oh, here's the actual result. So we can override that one with success. So this is a pattern of how you can do something, do some message, and update your response based on that. Lots of information, I know. Then we go back into I'll take a break in a second, the controller, and look at the ACK part. So in the controller, we are looking at the acknowledgement. And so this is interesting for me, this pattern here actually, right here. So when we acknowledge something, we get the original channel we sent it on. So we get both this packet. So when we get the acknowledgement, we get the original packet. We find the original packet that was sent, as well as the acknowledgement data. So we find the caller from the original, the packet, the source, I was the source of the packet, and the channel ID. So we can find out which channel I sent it on, right? When you get the acknowledgement, right, where did that come from? It comes from here. So you can find out which one is sent on, and then I take that original packet data to see what actually that packet was I sent a while ago. And then I can also parse the acknowledgement from the acknowledgement data, right? So you go with the original packet and acknowledgement. What it lets me do is the following. If the original package was dispatch, I'm going to expect a dispatch response. If the original packet was who am I, I'm expecting a who am I response. And the original packet was balances, I expect a balances response. So you see this nice pattern here. You just use the type of the original packet to figure out what I'm expecting as data in the acknowledgement. And it's a standard thing. So acknowledge dispatch does nothing right now. We should do something. Ideally, in a better version, this would call back and do some, trigger some callback to the original caller. So if you tell it to dispatch, when that comes back acknowledged, it would tell you, hey, original caller, this happened. Check it out, right? Right now we do nothing. But this callbacks is really something I'm working on in IBC Go right now, and a great thing to make it usable so some protocol can actually get the feedback. There's also acknowledge who am I when that comes. Basically, we parse this thing. If it is a result, we get the response, right? So this is basically match the type. If it was a success value, we parse it into a who am I response. If it was an error, then we just return an error message, right? And once we find the address, we say, hey, who's the original caller? What packet ID, remember what the channel was sent on? And then I can update it to set the remote address. So the first time it gets it, it sets the remote address on the other side. So once I get a response from who am I locally cache the address. It just never changes, right? So the who am I says, okay, I asked the size of who am I. So now locally, I can query that on the source chain. I have channel 17. What address is that? It doesn't have to do a new packet. It doesn't have to query it anymore. Once it did that one time on setup, it knows who its address is on the other side. And balances does the same other thing. It basically, parses the acknowledgement, make sure it's successful, right? Make sure it's successful, and then parse it into a balances response. And then it says update it. It makes sure it's the same address. Doesn't use a different address. If it uses a different address, it's a problem. And it will update the remote balances level. A remote address must not change. You can never change that number. One channel should have the same address all the time, but the balances will change all the time. So that is basically what it lets you do. So you can say, at this update time, I have this remote balance. This is actually not really correct here. I should not use my local block time on chain A. I should use the time that the acknowledgement is processed on chain B, right? So I send a packet at 11 o'clock, and on chain B, it's actually at 11:02, and I get the response at 11:05. It's not 11:05 update, it's 11:02 update, snapshot. But I'm not sure where the data is stored in this packet. Fault callbacks, so it might be lost on a lower level of what time the receiving blockchain processed it. I don't think is available in the application level, so we're just using it by this one. Maybe it's changed now. This is old code, so maybe in IPv3 this is exposed. I'm not sure, I have not checked that again, but you can just be aware the time is tricky. We have two different blockchains with different times and different heights. Anyway, that's the same thing. I'll take a little break now, and then like a question break for a few minutes, and then I'll show you the TypeScript stuff building on this. So, like 5 minutes. Food's gonna be a long time. I'll end up early. I'll just do another 20 minutes after this, and then I'll finish up. So it's not food time really now. It's more just a quick, you stretch a little bit. Just a few minutes of questions. I'll get into this. I'll do 20 more minutes on the TypeScript stuff. Then we're done. We have half-hour food break, or a little more, I think. All right. So look at this code. Poke around a little bit if you want to. It's on resources. There's a link to it. If you have any questions about something I did here, I covered. And that's a lot of information, but please, if you have questions, I'm sure if you're a little confused, I'm sure many other people are too. So please ask. Jake.
This is really cool. Wow. What do you think are some improvements that can be made to this for anyone who's interested in like hacking it's not hacking?
Very good question. So yeah, I just tried to clean this up with old code, and I wish I could do improvements on it. I didn't do any improvements. The first improvement I have is callbacks. So when on the controller, you have a message which says basically send messages, right? That's going to run on this channel, which must be owned by me, the caller. It checks I'm the owner of it. Run these messages. When it finishes, nothing happens to the caller. So it's fine if the caller is an external account. But if the caller's in the contract, it wants a callback, right? So it knows I did something, and so it should basically, I think, have some sort of callback hook, right? I don't know if it's just would be the simplest way, and you define some standard callback hook that is used, right? And if you set that to true, the original caller of this message, the original caller of it, will get this standard format with the original data response at the time. So I think that would be a simplest way of doing that callback. There's probably better ways of doing callbacks. You can invent that, but like some way of saying the original caller can get this data. Another one I think would be interesting is so interchain accounts is ordered channels, which I find to be really fragile. And so when you're discussing this, back a year ago, they were building one ordered channel between them. I said, this is problematic. Because if, Jake is moving lots of money, he's running the Juno Hack DAO or something like that, and they're moving lots of money in the dev DAOs and these big things, they're using this channel. Me, malicious guy, also sends a message in that channel, which is some illegal instruction, or some infinite loop, or some very expensive operation that caused 15 billion gas, right? Oh, that's packet number 5. Now Jake sends packet number 6, which is actually, staking his tokens. it can never be executed until mine's executed. So if we're sharing an ordered channel, it's very dangerous because I can stick something really dangerous or really slow to execute, really expensive, and it's going to block the entire channel until someone actually pays that gas or runs this thing. They can't do their own work. So sharing an ordered channel is very dangerous, right? So I said basically you cannot have one ordered channel. You have two choices. One unordered channel, like ICS 20, so everyone can share it, doesn't matter. If my packet never gets relayed, yours can still be relayed, doesn't matter. Or you have one ordered channel per connection. Per owner, every person has their own ordered channel. So the ICA team took that advice, I guess. They looked at them and they said they prefer the ordered channel, keep it, so they made multiple ordered channels, which is this design here. I made it unordered here because, well, TS Relay does not support ordered channels yet. I haven't done too much maintenance in the last year on it, so I haven't added that feature. I've done maintenance, but not added features. So I made that, but that also means you could combine them in one channel. So I'd be curious to see that as like one channel. Rather than making a different controller contract, you have one controller contract, you have one host contract, and depending whoever calls this one on the message, we say, oh, sender ID was this, which then figures out where you dispatch it on the other side. There's a different mapping. Rather than using a channel ID to map it, we use who the original caller was. Then we say, hey, when it finishes, we send this call back to the original caller, which makes it very easy to implement now. We create one channel, one setup, one time, and multiple contracts can call this thing. They immediately get an account on the other side, and they can, and then they can get callbacks when it finishes. It does mean there's a different step in registering account. So when you want a new account, the first time you have to register an account to get an address, and then wait for that to come back, which you get a callback saying register account message, get a callback when that finishes. And when it finishes, you can get a callback saying, okay, now I'm going to send another message that's going to actually do something, right? So I think callbacks are super important to get workflows going on. Those are my thoughts. I think a lot more stuff could happen on it. So that's just the first step, right? Like callbacks and combining into one channel. It makes it easier, I think, ease of use. And I think it's then, actually differentiates a little bit, having this one unordered channel and how important is ordered channels. Yeah.
So it's safe to have a constant reply ID even when you're going with relay. You don't need to have a custom reply ID. Does that make sense?
The reply ID you saw on the reply block, they are not in the relay, they're local. So the reply is only called, the reply method is only called locally as sub-message in the same transaction. That's a local call. There's two ways of getting callbacks, right? So if I send a message as a sub-message locally, right, in the same transaction, I will get a reply callback. If that reply callback, if uncaught errors or reply callback erroring, will revert the entire transaction, including what I did before that reply, before the sub-message. The whole transaction gets reverted, right? That's synchronous. In a way, it's active model, but it's some way in some sort of transaction that can roll back the whole transaction still, right? If you have cross-chain, you don't have that reply ID. You do send packet, receive ACK. Those are different calls. And the receive ACK, what I'm saying is you don't have that constant ID, you just match the original packet. So that's what I was showing you earlier, that match the original packet format, so you know what was happening, and that's how basically your ID is the original packet that got sent. Okay, any more questions here? So I think the other protocol is ICA. This is complex enough protocol here, I think, to be a real world example, right? This is like a major protocol. So you can look at how it's built as a contract. I think it's a starting place. And if you have another idea, like cross-chain swaps, you can probably modify this and not just accept any messages. Like, this is pretty generic. It doesn't know what it's doing. But you could actually make a protocol that says, I have a cross-chain swap protocol and query TWAP, and customize this maybe a bit. Use a lot of the same design, really, do some cross-contract calls in a limited scope, and maybe they have triggered more processing and different actions. Maybe they trigger a whole series of transactions on the other side based on state. So there's, okay, I'm going to move tokens, then I'm going to swap it, I'm going to check how much is returned, then return all the balances returned, and you can actually add logic and complex logic on the other side rather than just saying blindly run transactions. you could actually do various things here instead of this one and have much more complex logic on the other side rather than just run whatever they told me. It can actually process it internally. So I think that's a very interesting way. So you could basically fork this one, rip out this part and replace it with a bunch of more complex subcommands to do things like, move tokens over, swap them, return the results, and give me this average price back, whatever you want. And it would have to do lots of queries and things, combine them together and give you the results. So yeah, I think that's one way of also going to make another protocol here. Okay, I'm going to, without further ado now, I'm going to go over and check out the VS Code. So, yet another IDE here. Yeah, so I use IntelliJ. I recommend it highly for Rust development. I found the Rust extension very, very quick. It checks everything, underlines errors. It's very fast, and those inline hints are very useful. So if you look at this stuff, if you're not a fan there, this code here, where's the message? Contract. So here, you see these messages here and these arguments here. I found them quite useful, especially these type hints here, what's going on. And sometimes it says, oh, it's a result of something. I forgot to put the question mark at the end. If I do this, okay, it's a result. It's not a vector, it's a result. Oh, then I put a question mark here. So those type hints for me are super helpful. And I recommend using this if you're not addicted to another IDE yet and using Rust. I recommend this one. It's very helpful. Key bindings are a bit annoying sometimes. You don't know them, but it's very nice things. There's also a Rust extension for VS Code. You can use that one. It's good. I prefer this one, but it's also good. Anyway, VS Code, I use that for TypeScript. I think they're the best support I found for TypeScript. So that's where we are. Inside this, this whole repo here I showed you, there's this directory called tests. And tests is like a subdirectory inside this whole Rust repo, which is holding actually a package.json file, right? So we have a package.json file here, which is, its own IBC test. Oh, it's actually the wrong one. Yeah, I think I copied this from other demo I did. So basically, it's a package.json. I'll explain a few more things, but this assumes we have some local blockchain set up. We have TS Relay that has a bunch of test utilities in it. But I'm going to show you basically how we write the tests here. Let's close this, and I'll show you run the test later on, and then we're done. Then you have food. Promise, 15 minutes maximum. Thank you for your patience. So basically, we have a bunch of import statements here. We set the test utils. We set the osmosis fee here before. So this is set up. We store external contracts. We download CW and whitelist. And internal contracts, we have the ones here. I can run a command to build it locally, right? So I have a script there that will build these contracts. But the CI, what it does, it will first test the unit test the Rust code. It'll compile the Rust code to WASM, and then it'll execute the JavaScript test with that WASM I just wrote. So if I break the Rust code, I change it in a modified way, it will actually first make sure all the local Rust tests work, then it'll load in blockchain to run a full integration test with that same WASM I just had, which is pretty cool. I thought it'd take forever. Running a test run in about a minute or two, or 2 minutes maybe, which is, I think, pretty good to run the whole battery of Rust tests, compile it, and after you compile it, you run the integration test with multiple blockchains, which is, I think, pretty good time, actually. Anyway, it's not 1 second feedback, but pretty fast feedback to know if you broke a whole protocol. So the before block basically says, you go upload stuff. I create a WASM client here, and I call these contracts. I say, basically, I want this contract controller. I take this file here as controller. And on the osmosis side, I need the host contract, and I need this whitelist contract, right? And so I do this one time to upload all the WASM files onto the 2 blockchains I have. Local blockchains, not real blockchains. That's too expensive. And then, so the setup one, the first test is this. I'm just going through it really quickly. Let's maybe close. How to get smaller? There. So the first test is this. Basically, you set up a WASM client, and you call instantiate. We have the addresses now. So it says instantiate it has WASM. This basically is a helper method in TS Relayer that will create a new account and fund it. So it creates a new account with 4 WASM or something on it, tokens on it. So a few tokens on it. You say, hey, create an account using this controller contract, right? The initialization message is nothing, and you label it with auto fee. Boom, it's created. And we verify, we get the port of it, we pull the port out, we get contract, and we can query the port of it for the controller port once it's created. It's synchronous, so it finishes. This makes an osmosis client with funds. It then says, okay, instantiate the host contract, right? But it tells the host contract what the waitlist ID is. So later on, it knows how to make those, right? We create these contracts, we use 3 IDs. This is a reflected ID, we don't create it yet. It will be created by the host contract. Verify it doesn't get the host port. And then this here is basically saying a relayer. So those Osmo and WASM clients, right? Those are basically users. That's my user and my user I have there, right? This is in the relayer. So this creates a relayer setup. We'll take 2 blockchains, I'll fund them, and it'll create a relayer that knows what these 2 blockchains with accounts. Then you pass into link create new connections. That is a great CI one. It basically says create a new client and create a new connection. And that link is creating 2 accounts on different blockchains. Those blockchain definitions, a new client and a new connection between those blockchains. And that's called a link. That link is like the high-level thing in our library for TS Relayer. It allows you a whole lot. And then link create channel starting on side A. You start inside A or B, right? The first one here is A, so WASM D is A and Osmosis is B, right? We put them in that order. This is A. Using controller port on side A, host port on side B, Osmosis, unordered channel, and using the version string. So these 3, with a wait, of course a wait, right? So these 3 things say create some accounts, create a channel, and then create a client and connection and create a channel with my things. And this verifies that actually works. So that's, I think, pretty easy to run Relayer. Now, this is just the original setup function. We verified it worked, right? Another one is actually, when I want to do other ones, I want to build on that. I don't want to write the same code over and over and over again. So I pull this basic test code out into something called demo setup, so the demo mode, and I basically store the information, who the WASM client and Osmo client for my user is, right, me, the controller port ID, the host, I think these are channel IDs actually, no, yeah, the controller is then the address, yeah. So this is the address of the controller address on the WASM side, the address of the host on the Osmosis side, the link, which is basically the relayer knowledge, and an ICS-20 connection. So why have 1 channel? We have 2 channels, right? So the setup here, same thing, we instantiate the initialization, we instantiate the host. We do set up a link, we create a new channel, client and connection. We create a new channel for controller port. And then we say, let's create another channel. Let's create another channel, which is using the ICS-20 ports of both chains, unordered with ICS-20-1. So we create an ICS-20 connection as well. So on that same connection, we have 2 channels, the relay is running. Both are custom channel between our two contracts we wrote, and an ICS-20 from the standard transfer one. And returns all the information here so we can do things in test cases. All the test cases then basically do the same thing. They do the demo setup to start up, to configure the whole thing, configure the contracts in the relayer. And what do? The first thing, remember the packet, the who am I packet we had, right? The who am I packet we launched. So first you want to relay that one. So if you want to relay it, do relay all. Relay all will say, I take all packets from side A, I relay them to side B, and return the acknowledgement to side A. Then I take all packets from side B, pending, I relay them to side A, and release the acknowledgement to side B. That's what relay all does. It's everything for you. And it returns the info. Info is the acknowledgements, how many packets were relayed, right? And so then you can say, okay, I'm asserting package from A, it's a helper function I wrote, which says basically this information here is saying there's one packet relayed from A, and it was successful. So I said I'm relaying the packet, and I said, oh, yeah, you did relay one packet and successful. So I know there's actually a packet on the wire, and it did not fail. So that's 2 lines of code. Pretty easy. And I've actually then run the whole thing on both blockchains, the whole who am I. And after it's done, I say, okay, it succeeded. Now that contract should be registered, so I can find the WASM, I query the WASM controller, I get the account listing, and I find the remote address of my channel, and I find my channel IDs here. I can show the accounts, I can find all the balances, I can find the information on it, right? So I can start querying it because I know who the other one is. Then you can basically say, okay, I'm going to send some money to the remote address. So I see my balance. I'm sending money here, fund remote account, which we go into it, is basically using the send funds. So I'm going to send funds to my account on the other side. It will actually, the controller will trigger ICS-20 and send funds on the ICS-20 transfer packet. Yeah, I know. Anyway, it will do that one. It sends tokens, and then, so we fund the remote account, and we relay that packet, which will actually move money, right? Then we say, we can get the balance we had. Then we can check the remote balance, which says, from, again, WASM, I call Osmo, what's my balance, get the number back, and I can find out that my balance was actually done on the other side. So these are, every time I want to do another message, I basically do a function call here, a method call on the local contract, on the controller side, relay everything, make sure it did succeed, right? So make sure it didn't fail somewhere in the relaying, or got an error in the relayer. And then you check to see the state was updated properly. The same thing, you have control action on the chain. I'm going to stop, I know. Control action on the chain. So you actually just, I moved money on the Osmo side directly, and then I basically say, okay, remote bank send, saying, tell the chain to move money from my account on WASM, from Osmosis to another account on Osmosis. So I set this up, and whatever, these 30 lines here is basically doing that connection and everything there. I think a lot of people are hungry. I'm going to run in the background. I'm going to show you how to run some tests on it. But if you're interested, what I'm going to do is I'm going to start up. I'm going to stop talking, and I'm just going to watch these terminals here. If you want to get up and start eating, get up and start eating. We have half an hour break now. And I'm going to continue and just show you how to run it. You can check out this repo and run it. But basically, you create 2 local blockchains. You run Osmosis blockchain and WASM blockchain on the local host. And then you can run npm run test, and it will do this whole setup here. Yeah, I'm running on a MacBook, and it's simulating AMD. There's a little limits here. So if you are a MacBook, the problem is you have Intel-based binaries running on a MacBook and simulating Rosetta. And so when you're running Osmosis with WASM contracts through Rosetta, you use a lot of memory. And Docker seems to kill it now and then because it's using too much memory and it hits a Docker limit. So I'm going to try to actually adjust my limits on Docker first and then see if I can get this to run. It's usually running about 4 tests and then crashing out of memory, and the Osmosis binary will die. But if you're using Intel-based thing, it does not happen. If you actually compile Docker images for ARM, it works better. Just letting you know, there's a few tricks. But yeah. You can get up and ask questions if you want. I'm just going to do it in the background, show you how to run this stuff. So I'm going to give it a little memory here. Let's see if that works. So I'm going to give Docker a little more memory to see if it will be a little more robust than last times I've been testing it. Yeah, you can have food. So I'm not going to talk, I'm just going to be running stuff. You can watch the screen. I'll keep recording it maybe, showing this. I'm going to be showing the screen. You can see some of these commands running, some npm test commands, and see the stuff run.